So just as a refresher from our last video, we were talking about band gap and electron hole pairs. We said at 0 Kelvin we cannot have any free electrons because they're all bound to the atoms. But as our temperature rises above 0 K, we can have thermal energy, and if it's sufficient, our electron can break away from our atom and move throughout the crystal lattice. We said there's two ways that we can represent this, and last time we looked at our 2D bonding structure. Now we're going to look at our second way, which is our energy band diagram. So there's going to be a lot of new terminology. I'm going to try to write out in writing what it means after I sort of first introduce it here. This is another topic where we could spend a lot of a class on, but we're just going to briefly talk about it. So we have sort of two bands, two energies that are important in our band diagram. On the top we have our E sub C, which is the edge of our conduction band. And so our conduction band is going to start at this value E sub C, and it's going to extend up to higher energies. Our other value on the bottom, E sub V, is the top edge of our valence band. So our valence band goes from EV down to the lowest energies, so getting closer and closer to the nucleus of our atom. The difference between these two levels is called our band gap. So between here and here, we have our band gap energy, which we have is Eg. And so this is our forbidden band gap, and I'll talk about why that is here in a second. So ideally, we don't have any energy states in this forbidden band gap. So let's just write here, so ideally, no energy states. And so the analogy I like to give is, let's say I'm standing in a classroom with a desk. I either have my feet on the floor. If I have enough energy, maybe I can jump up and I can get my feet on the table, but there's nowhere in between the floor and the table where my feet can be and be in a stable state. So it's either sort of one or the other. I'm either in the floor, which would be like our valence band, or if I have enough energy, I can jump up to the table, which is like being in our conduction band. In practice, however, there are going to be some forbidden states in here, but again, that's a topic that's beyond the scope of this course. So ideally, we have no states here, and so our electrons are going to be in the valence band for our 0 Kelvin case, but when they have thermal energy, they can move up to our conduction band. So let me just write this real quick so we can say our electrons in the valence band are bound to the atoms. Okay, so that represents when they're in the valence band, they're still bound to the atoms, but once they move up to the conduction band, they're free to move throughout the crystal. So electrons in our conduction band can move through our crystal or move through our lattice. Okay, and of course, once they're up there, they can contribute to our current. So what does that look like pictorially here? Well, let's say we have some electron down here and it has enough energy. So here we have all of these electrons. And let's say maybe one of these guys has enough energy, so it's going to jump across this band gap, and we now have an electron up here in our conduction band, which can contribute to the current. So of course it's left our valence band, and in doing so, we're again going to leave behind this net positive charge, which we call a hole. So our electron is going to be creating current by moving around in our conduction band, and our hole is going to be contributing to current by moving around in our valence band. And again, we're not going to be worried about the specifics of that in this course, but just something to be aware of. So I want to talk a little bit more about our band gap real quick. So our band gap is just a material property. So this is Eg. So this is a material property. And so as I've mentioned, this is called the band gap. for obvious reasons, because it's the gap between our valence and conduction bands. So different materials are going to have different band gaps. So typical values for semiconductors. So semiconductors, see if I can spell that right, you'd hope so. So semiconductors, typical values are going to be about 1 electron volt. Larger band gaps are going to correspond to insulators. So larger, e.g., so by larger I mean maybe about 8 eV, would correspond to insulators. So insulators such as oxide. So a common one in electronics would be a silicon dioxide, for example. So there is some in between here as well. So again, sort of just another thing to mention we're not going to focus on, but there's something called wide band gap semiconductors. So wide band gap semiconductors. And so these have applications in high power areas. So high power areas are typically going to have these wide band gap semiconductors, so we can abbreviate this, wide band gap. And so these are going to be between this 1 eV and the 8 eV, so anywhere from like 3 to 6 eV. Some common materials that you'll see are silicon carbide, which we've mentioned before, gallium nitride, so gallium and nitrogen, and also there's some research looking into using pure carbon in its diamond bonding form for wideband gap semiconductor applications. So let me take a step back and point out this unit I've been using. So I've just thrown out this unit electron volt, and you might or might not be familiar with that. So let me just mention really quickly, this EV is our electron volt. And so typically this is used to describe energies in semiconductor physics just because they're really small. So let me just give you the definition real quick. So 1 EV is the energy required to move an electron through a potential difference of 1 volt. So the energy to move 1 electron through a potential difference of 1 volt. And so we could relate this to a more common form of energy, joules. So 1 electron volt is approximately 1.6 times 10 to the minus 19 joules. Okay, so one last topic I want to talk about with our intrinsic semiconductors is, we've kind of already touched on this a little bit, but just to formalize this, is for an intrinsic semiconductor, every electron is going to have a corresponding hole, excuse me. So intrinsic semiconductors, so electrons and holes are only generated in pairs. And so of course we're going to come back and we're going to contrast that when we look at our extrinsic semiconductors, but for now we've only seen how these things are generated in pairs. And so what that means is for every electron there's a corresponding hole, and of course vice versa. So what that means is that both have the same density in our crystal lattice. And so that's going to be a useful thing to know, because as we look at our current equations a little later on, we're going to see that our current equations are related to our densities of these charged carriers. So this density right here, which is again the density of our electrons and our holes, has a special name. So this is called our intrinsic carrier concentration. And so typically our symbol for that is going to be N sub I, so our intrinsic density. And so the equation for that is our intrinsic carrier concentration, N sub I, is equal to B times T to the 1.5 exponential of negative EG divided by 2KT. And so let me write out what each of these variables are. So our B is just going to be some coefficient related to a semiconductor material, and so we're not going to worry about going into depth. That's something we would look at a little bit more if we were in a more advanced class, but this is just a coefficient for a specific semiconductor, and I'll give you some values and they're in your book as well for some common semiconductor values. So our T is our temperature in Kelvin, and so recall that our temperature in Kelvin is just equal to our temperature in Celsius plus 273. Our EG, as we just talked about, is our band gap. So our band gap, and of course remember that is related to a specific semiconductor, so that's sort of a material property. K is our Boltzmann constant, and so we'll see we'll give you some values here in a little bit, but depending on the situation, we have a couple different values that we can use for that. So we can say our K is equal to 8.6 times 10 to the minus 5th EV per Kelvin, or if we want to use different units, we can say it's equal to 1.38 times 10 to the minus 23rd joules per Kelvin. And so that's just using this conversion factor up here for our EVs to Kelvin. So let's look at some values for some common semiconductors. And so again, this table is in your textbook, but I just want to mention these here, and we'll look at an example in the next video. So we're going to look at the material, our band gap in EV, and then that coefficient B, which is going to have units of per cubic centimeter per Kelvin to the minus 3/2. Okay, so material, silicon, of course, we want to focus on. Another common semiconductor material, compound semiconductor, is gallium arsenide. And then another group 4 semiconductor is germanium. So for silicon, our band gap is 1.1 eV. For gallium arsenide, it's a little bit larger at 1.4. And for germanium, our band gap is a little smaller at 0.66. This B coefficient, 5.23 times 10 to the 15th for silicon, 2.10 times 10 to the 14th for our gallium arsenide, and 1.66 times 10 to the 15th for our germanium. And so a couple of things that we can note from looking at these units is we see this B has units of per cubic centimeter. The Kelvin to the minus 3/2 is going to cancel out with the Kelvin here. We want to make sure that whatever K we're using here, a Boltzmann constant, the units agree with this. So for instance, if we have our band gap in electron volts, we want to use our Boltzmann constant that has electron volts. So that ultimately what we're going to have, typically we report this as units of per cubic centimeter. So that means we have so many electrons per cubic centimeter, or so many holes per cubic centimeter. And so we're going to see in the example on the next slide that based on primarily this band gap and the temperature, we're going to have different concentrations for different materials.